Let's look at the following problem on an undirected graph. So you're given an undirected graph with n vertices which represent n cities, and the edges between pairs of cities represent the cost of directly connecting those cities with roads. So for example, this particular edge between cities E and F has a cost associated with it, and this cost is 5, indicating the amount of money that has to be spent in order to build this road between E and F. So this kind of a graph is called a weighted graph, where the edges now have weights on them, and it's also undirected because these roads are assumed to be bidirectional. Now we want to link together all these cities in a way that there is a path between every pair of cities. So it should be possible to start from any city and go to any other city, but we don't want to build all the roads that are shown on this diagram. We want to spend the minimum amount of money that is required to link all these cities together. So we want to find the minimum cost way of connecting all the cities together. Now all the edge weights here are assumed to be positive because there is a positive cost associated with constructing any road. And the question we have to ask ourselves is, what subset of roads, what subset of these potential roads shown in this diagram should actually be constructed so that all the cities are linked together and we should have spent the least amount of money. So one option could be to choose these roads. We choose this road between A and B, this road between B and D, this road between B and C, this road between D and F, and this road between E and F. So if we decide to construct these 5 roads, we would have linked all the cities together. The total cost of building these roads would be 4 plus 4 plus 4 plus 6 plus 5, which is basically 23. Now, is this the best that we could have done? Well, the answer is clearly no, because instead of choosing this road and this road, we could have chosen these 2 roads which have a lower construction cost, and we would have still linked together all the cities had we chosen these subset of roads. So these yellow roads that I've shown in this diagram would take a total cost of 1 plus 4 plus 2 plus 6 plus 5, and that amounts to a total cost of 18 units. So this is clearly better than the previous solution we had, but is this the best possible solution? Well, maybe not. Maybe we shouldn't have chosen this road with weight 6. Maybe we should have tried to connect C and F together by building this road of length 4 or cost 4. So we have to design a general algorithm which will decide what subset of edges or what subset of roads to build which link together all these cities with the minimum cost. Now if you think about it, any subset of edges that we choose which is part of the optimal solution cannot have cycles in it. Why should there be no cycles? Well, because if there was a cycle, then there would be a redundant connection which could be dropped without affecting the connectivity. So let's say we have a cycle here involving these 6 vertices. Now even if we remove one of the edges on this cycle, let's say we remove this edge, the remaining cities would still be connected overall. So removing cycles does not disconnect the cities from each other. And so if we are looking for the min cost way of connecting all the cities together, clearly the subset of edges that we choose cannot have redundant connections, so there should be no cycles. Secondly, that subset of edges should span all the vertices, right? They should include all vertices. So this road network needs to span all the cities in a way that all the cities are connected to each other. There should be a path to start from any city and go to any other city. So we are really looking for a structure that is connected, which has no cycles, and which spans all vertices. This kind of structure is called a spanning tree. So a spanning tree is a tree which means it is connected and it has no cycles and it spans all the vertices. Moreover, there can be multiple different spanning trees. We just saw that there could be at least 2 or 3 different spanning trees we might have chosen for this example. What we really want is the spanning tree which has the overall minimum cost. What is the cost of a spanning tree? Well, it's just the cost of constructing each of the roads which make up the spanning tree. So we just have to sum up the weights on the edges which are part of the spanning tree to get the total cost of that spanning tree. And this is an optimization problem where we want to design an algorithm that will return to us, given a graph that is, let's say, initially connected, it will return to us the minimum cost spanning tree corresponding to the min cost way of connecting all these cities together. Now this minimum spanning tree problem could be defined similarly in other contexts as well. Maybe these are not cities we are looking at, maybe these are electronic components on a chip, and we are thinking of laying down wires that will connect all these components together in the min cost way. So if the cost of laying down a wire is proportional to the length of that wire, then basically we want to minimize the total length of the wire used to connect all these components together so that we minimize the total cost. Now, how many edges will there be in any spanning tree? So if we visualize each city as a vertex, then every time we build one of the roads that falls into the spanning tree, we are linking together 2 cities or 2 vertices in this graph, and every time we add an edge, we are basically reducing the number of connected components by 1. And so if we want to link together all the cities in a way that we don't get a cycle, then notice that we need to add n minus 1 edges to bring down the number of connected components from n down to 1. And we've seen this before in the context of doing union find operations, that the maximum number of union operations would be n minus 1. Well, here we need exactly n minus 1 operations because we need to basically connect all the cities together. So every time we build a road, we are reducing the number of connected components by 1, and at the end our spanning tree should have exactly n minus 1 edges, should not have more, because if it has more, that would be a redundant connection. Now if we try to do this in a naive way, let's say we are given m edges in the graph, a naive way to solve this problem would be to choose a subset of n minus 1 edges out of the given total set of m edges, and then just see if it makes up a spanning tree or not. If it does, note what its cost is, and then move on to the next subset of size n minus 1 from those m edges. And at the end of this whole process, we just compare notes and see which spanning tree did we build with the minimum cost, and pick the one that corresponds to the minimum cost. So that would take a lot of time. Even if m was, let's say, twice n, right? Let's say it's a sparse graph where the number of edges is twice the number of vertices. This 2n choose n minus 1 would still be a number that is exponential in n. And if you've gone through the dynamic programming module, you may remember that finding the value of n choose k in a naive way was leading to an exponential time complexity, because many of these values are actually exponential in n. So it's not important for you to remember that clearly to understand this video, but if you just want to understand why this is exponential, you could go back to the analysis that I had done in some of the videos and classes there. But the basic lesson here is that there is potentially an exponential number of spanning trees to consider, and so we can't just enumerate all possible spanning trees or all possible subsets of edges of size n-1 and choose which is the best. That might work, it would be a correct algorithm, but it would be an exponential time algorithm. So we don't want to go in that direction. We want to build an efficient graph algorithm.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today